Try to imagine nothing. Go ahead. Close your eyes and try to visualize absolute emptiness. You probably see a black void, maybe some stars in the distance if you're feeling romantic, but essentially you picture a vacuum. You think of space as a stage, a big empty box where stuff happens. You put a planet here, a star there, maybe a confused astronaut floating in the middle. But the space itself, to you, it's just the container. It's the absence of things. I hate to break it to you, but that container doesn't exist. The idea of empty space is the greatest hallucination of the human mind. The universe isn't a box, it's a glob of jello. Okay, maybe not literal lime-flavored gelatin, but physically speaking, you are walking through a medium that is constantly being twisted, squashed, and pulled. When you look at the air in front of you, or the vacuum of space, you aren't looking at nothing. You are looking at a field. And until you understand what a field is, you don't understand physics. You're just memorizing rules for a game you don't know how to play. Let's start with something you can actually touch. Imagine a big, wobbling block of elastic material, a giant cube of jello sitting on a table. Now, suppose I reach in, grab a tiny speck of dirt trapped inside that jello, and I pull it. The jello distorts. It stretches. If you want to describe what happened to that block, you can't just say, it moved. That's lazy. You have to describe how every single point inside that block shifted relative to every other point. We call this strain. If I pull the corner, the middle moves a little, the far side moves barely at all, and the point under my finger moves a lot. To describe this mess, we need numbers, a lot of numbers. For every tiny point in that jello, we need to know how much it stretched sideways, how much it stretched upwards, and how much it stretched forward. And it gets worse. We need to know if it twisted. Did the top slide right while the bottom slid left? That's a shear. Suddenly, this innocent block of jello is a mathematical nightmare. To fully describe the stress and strain inside it, we can't just use a single arrow. We need a concept called a tensor, a beast of a mathematical object that packages all these stretches and twists together. But here's the beautiful part. This isn't just about jello. This is how the entire universe works. Physics is the business of assigning numbers to points in space. That's it. That's the job. If you assign a single number to every point in space, like, say, the temperature, you have what we call a scalar field. Imagine a block of metal that's hot on one side and cold on the other. You can close your eyes and point to any spot inside that metal, and there is a specific number waiting for you, 20 degrees. Move an inch left, 25 degrees. The temperature doesn't jump around randomly. It changes smoothly. It forms a landscape. Now, imagine drawing lines connecting all the points that have the exact same temperature. You get these invisible surfaces, like the contour lines on a topographic map. We call them isotherms. They are imaginary, but they tell you the shape of the heat. But a single number isn't enough for the interesting stuff. Sometimes, the universe has an arrow at every point. Think about a rotating object, or water flowing in a river. At every single point in that river, the water has a speed, but it also has a direction. It's going somewhere. You can't just say, the water is moving at 5 miles per hour. You have to say, 5 miles per hour downstream. This is a vector field. Imagine the room you are sitting in right now. The air seems still, but it isn't. There are tiny currents everywhere. If you could freeze time and attach a tiny little red arrow to every molecule of air showing where it was going, the room would look like a porcupine. That forest of arrows is a field. Heat flow works the same way. Heat doesn't just sit there. It flows from the hot spots to the cold spots. So, superimposed over your map of temperature numbers, there is a map of heat flow arrows. And here is the rule. The heat arrow always points downhill. It wants to get away from the hot zone as fast as possible. Now, we need a way to connect these two things, the temperature numbers and the flow arrows. How do we find out which way the heat will flow just by looking at the temperature map? We use a mathematical machine. We call it del, which is just a fancy name for a symbol that acts like a meat grinder for functions. You feed it the map of temperatures, and it chews it up and spits out a map of arrows. This operation is called the gradient, and it is exactly what it sounds like. If you are standing on a hillside in the pitch dark and you want to know which way is up, you feel around with your feet. You find the direction where the slope is steepest. That direction is the gradient. The gradient of the temperature tells you the direction of the hottest change. It tells you, if you want to get hotter, go that way. And the heat flow? It simply obeys the opposite of the gradient. It runs down the hill. But nature isn't satisfied with just flowing down hills. Sometimes nature likes to spin. Imagine you have a field of arrows that looks like a whirlpool. The arrows aren't flowing out from a center, they are circling around it. If you dropped a leaf in there, it wouldn't just move, it would rotate. To measure this swirliness, we use another operation called the curl. If the gradient measures the slope of the hill, the curl measures how much the field is twisting. It tells you the rotation. And then there's the divergence. This measures how much the stuff is spreading out. If you have a nozzle spraying water, the divergence is high at the nozzle because water is exploding outward. If you have a drain, the divergence is negative because water is vanishing into it. Why am I telling you about hills, swirls, and drains? Because these three concepts, gradient, curl, and divergence, are the language of reality. Maxwell's equations, the laws that govern light, electricity, are just sentences written in this language. They say things like, the divergence of the electric field is the charge. Translation, electric charge is a sprayer that shoots electric field arrows outward. Or, the divergence of the magnetic field is zero. Translation, there are no magnetic sprayers, no magnetic charges. Magnetic lines never start or stop. They just loop forever. Speaking of magnetism, this is where things get really weird. You think you know what magnetism is. You played with magnets as a kid. You know they stick to the fridge and hate each other if you flip them around. But have you ever asked why? Why does a wire carrying an electric current suddenly turn into a magnet? Let's look at the force on a moving charge. We call it the Lorentz force. It's the rule that says if you shoot a charged particle through a magnetic field, it gets pushed sideways. Not forward, not backward, sideways. It's a force that acts perpendicular to the motion. That's bizarre. Gravity pulls you down. Electrical attraction pulls you closer. But magnetism pushes you sideways, like a rude pedestrian shoving you into traffic. The standard explanation involves the right-hand rule. You hold up your hand, point your thumb, curl your fingers, and look like you're trying to hail a taxi while doing yoga. It works, but it's arbitrary. Nature doesn't have hands. Here is the truth. Magnetism is not a separate thing. It's just electricity seen from a moving perspective. Imagine a copper wire. Inside, you have positive copper ions fixed in place, and a sea of negative electrons flowing through them like a river. This is the current. Now, imagine a single negative charge moving alongside this wire at the exact same speed as the electrons inside the wire. From your perspective, standing still in the lab, you see a current. You check your rule book and it says, currents create magnetic fields. Okay? The magnetic field pushes the moving charge toward the wire. Simple. But wait. Let's look at it from the perspective of the moving charge. If you are the charge, you are looking at the electrons in the wire, and they look stationary relative to you because you're moving at the same speed. If they are stationary, there is no current. If there is no current, there is no magnetic field. So, if there is no magnetic field, the force disappears, right? The charge should drift away? Wrong. The charge still gets pushed toward the wire. But how? If the magnetic force vanished, what is pushing it?
Einstein steps in. You see, when things move, space itself contracts. It squishes. This is special relativity. From the perspective of our moving charge, the positive ions in the wire, which were stationary in the lab, are now rushing backward. Because they are moving, the distance between them shrinks. They get packed denser. Meanwhile, the electrons in the wire, which are moving with us, appear stationary. Their spacing relaxes. They spread out. Do you see what just happened? The wire, which used to be electrically neutral, now has a higher density of positive charges and a lower density of negative charges. To the moving particle, the wire has suddenly become positively charged. It's not magnetism pulling the particle in, it's good old-fashioned electric attraction. The particle sees a positively charged wire and wants to hug it. So, what we call a magnetic field in the lab is just an electric field disguised by relativity. It's what happens to electricity when you start moving. This connects back to our vector fields. We said earlier that fields define the force on a charge. We have an electric field vector and a magnetic field vector. What we just discovered is that these aren't two different actors. They are the same actor changing costumes depending on how fast you run past the stage. If you stand still, you see electricity. If you run, you see a mix of electricity and magnetism. They are components of one giant four-dimensional object, the electromagnetic field. But there is a catch. To make this work, charge has to be indestructible. Think about the conservation of charge. It's a fancy way of saying charge is conserved. You can't create electrons out of nothing, and you can't make them vanish. If a current flows out of a box, the amount of charge inside the box must go down. It's basically accounting. If charge wasn't conserved, if it could change depending on your speed, the whole universe would break. Imagine heating up a block of metal. The electrons speed up. If their charge changed because of that speed, the block would suddenly become electrically charged just because it got hot. Massive sparks would fly every time you made toast. Since your toaster doesn't kill you, usually, we know charge is an invariant scalar. It's the same number no matter how fast you go. Now, let's go back to those magnetic field lines. Remember, the divergence of the magnetic field is zero. No magnetic charges. This means magnetic field lines have to form closed loops. They are like rubber bands that never break. If you have a straight wire, the field lines circle around it. If you have a loop of wire, the field lines thread through the middle and wrap around the outside, looking like a donut. This creates the magnetic dipole. It's the basic unit of magnetism. You don't have a north pole and a south pole sitting separately. You have a loop. The north is just the side where the lines come out, and the south is where they go in. But here is a question that should bother you. Where do the lines go when they hit the end of a bar magnet? They don't stop. They go through the magnet. A permanent magnet is just a solenoid that doesn't need a battery. Inside that iron bar, billions of tiny electrons are spinning. Each spinning electron is a tiny current loop. In iron, these loops decide to line up and sing in the same choir. The result is a macroscopic magnetic field. So there is no magic magnetic fluid inside the iron. It's just currents, permanent atomic currents that never stop flowing. But we are still describing this with lines and loops. Is that what's really there? Are there invisible spaghetti strings filling the room? Of course not. The lines are just a drawing tool. What's really there is something called the vector potential. And this is where we have to abandon the high school pictures entirely and look at the machinery under the floorboards. Because it turns out the magnetic field might just be a shadow of something more fundamental, something we call A. We left off with a cliffhanger. We stripped away the magnetic field lines and realized they are just cartoons. We realized that magnetism and electricity are the same thing, just viewed from different speeds. But if we want to actually predict what the universe will do next, if we want to see the machinery under the floorboards, we need to talk about the ghost. We need to talk about A. In the simple world of electrostatics, life is easy. You have a scalar potential, voltage. It's like height on a topographic map. If you know the voltage everywhere, you just roll the ball down the hill, and that's your electric field. Simple, intuitive. But magnetism is a headache. It doesn't act like a hill. It acts like a whirlpool. It swirls. So we can't represent it with a simple scalar number like height. We need something with direction. We need a vector potential. We call it A. Think of A as the momentum of space itself. Imagine a river. The water is flowing. That flow is A. If you drop a leaf in the river, it moves with the flow. But if you stick a paddle wheel in the river, it spins. That spin, that's the magnetic field. The magnetic field B is just the turbulence that happens around the edges of the flow of A. For a long time, physicists thought A was fake. They thought it was just a bookkeeping trick, a mathematical shortcut to calculate the real magnetic field. But then quantum mechanics came along and ruined the party. It turns out you can shield a particle from the magnetic field completely, hide it behind a lead wall where the magnetic field is zero, and the particle still feels something. It feels the river of A flowing past the wall. The ghost is real. In fact, the ghost is more fundamental than the thing it haunts. The vector potential is the primary fabric of electromagnetism. The magnetic field is just its derivative. Now I want to pivot. We've been talking about fields as if they are these ethereal, magical clouds hanging in the void. But to truly understand the vacuum, you need to stop thinking of it as a cloud. You need to think of it as a solid object. You need to go back to the jello. When engineers study solid materials, steel, concrete, rubber, they use a branch of physics called elasticity. And when we study the vacuum of empty space, we find the exact same mathematics. Consider that glob of jello we talked about. Suppose you twist it and squash it. To describe the internal torture of that jello, you can't just say it's under pressure. Pressure is too simple. It pushes everywhere equally. But in a solid, you can push on one face while pulling on another. You can twist the top while holding the bottom still. We describe this internal mess with a stress tensor. Don't let the words scare you. A tensor is just a box of numbers. If a vector is an arrow, a tensor is a machine that takes an arrow and twists it. The stress tensor tells you exactly how much force is acting on every possible surface inside the material. It tells you, on the top face, we are pushing right. On the side face, we are pulling down. And how does the material respond to this stress? It deforms. We call this strain. If a tiny speck of dust inside the jello moves from point A to point B, that's displacement. But strain is subtler. Strain measures how the neighbors of that speck moved relative to it. Did they get closer? Did they drift apart? Did they rotate around it? This is defined by the strain tensor. It's the map of the distortion. Why am I talking about engineering concepts in a script about the universe? Because energy doesn't care what it's made of. When you squeeze a spring, you store energy. When you shear a block of metal, you store energy. The amount of energy stored depends on a very simple rule. Stress times strain. How hard you push, multiplied by how much it moves. This is true for a rubber band, and it is true for the vacuum of space. An electric field is a stress. A magnetic field is a strain. The empty space between the stars is loaded with potential energy. Stored in the electromagnetic fields exactly like elastic potential energy is stored in a twisted steel beam. This is why light exists. If you kick a block of steel, a wave travels through it. We call it sound. The speed of that sound depends on two things: how stiff the material is, how hard it fights back, and how heavy it is, how hard it is to move. If you kick the vacuum, a wave travels through it. We call it light. And the speed of light? It is determined by the stiffness of the vacuum and the density of the vacuum.
You have probably seen the constants epsilon 0 and mu 0 in physics textbooks. They look like boring numbers. They are not. They are the elastic constants of the vacuum. One tells you how hard space fights back against electric stress, stiffness, and the other tells you how much magnetic inertia it has, density. Light travels at c, not because it's a cosmic speed limit imposed by the police, but because that is the speed of sound in the solid block of nothingness we call the universe. But here is where the analogy gets really fun. Real materials aren't perfect. If you pull a spring too hard, it snaps. Take a piece of blackboard chalk. If you hold the ends and pull, it snaps in half. If you look at the break, it's a clean, flat cut, perpendicular to the pull. Why? Because chalk is brittle. It is weak in tension. It cannot handle being pulled apart. But now, take another piece of chalk and twist it. It doesn't snap straight across. It breaks in a spiral at a 45-degree angle. It looks like a corkscrew. Why? You didn't pull it, you twisted it. You applied a shear. But the math of tensors reveals a secret. A shear is just a tension in disguise. When you twist the chalk, you are actually creating a line of maximum tension running at 45 degrees along the surface. The chalk finds this hidden tension and snaps exactly along that line. Nature is full of these hidden mechanisms. The geometry of the stress dictates the geometry of the failure. Does the vacuum of space have a breaking point? Can you pull on the electric field so hard that space itself snaps? In classical physics, no. But in quantum electrodynamics, yes. If you create an electric field strong enough, a critical field,
You can literally rip particles out of the vacuum. You can tear the nothing apart and create electrons and positrons out of pure stress. The vacuum isn't just a stage. It's a material that can be stressed until it breaks into matter. So, let's revisit our opening question. What exists between the object? The answer is everything. The quantum vacuum is not empty space. It is a plenum. It is a solid medium. It is a playground of fields described by vectors, scalars, and tensors. It has a temperature. It has a flow. It has stiffness. It has inertia. It has momentum. It can be twisted, sheared, and stressed. It stores energy. It carries waves. Understanding physics isn't about memorizing that gravity pulls or magnets attract. It's about learning to see the invisible scaffolding. It's about realizing that a differential equation isn't just algebra. It's a set of instructions for how the jello wobbles from 1 millimeter to the next. Einstein didn't invent a new language to describe gravity. He just borrowed the language of geology and structural engineering. He looked at the universe and realized that space-time is just a giant, bendable solid, and gravity is just the strain tensor of the cosmos. So, the next time you look at the night sky, don't see emptiness, don't see a void, see the fields, see the tensors stretching and squeezing in the dark, see the huge invisible river of vector potential swirling around every wire and every atom. The universe is a crowded place, and the nothing is the heaviest thing in it.
Let's talk about something that sounds ordinary, almost boring, yet sits underneath nearly everything physics says: the idea of a state. A state sounds like a condition, a description of how something is right now. But in physics, it carries a precise meaning. A state is the full physical situation of a system, written in the smallest amount of information needed to determine what can happen next. Physics has a strict rule here. It does not care about how a system arrived where it is. It only cares about how it is right now. If two situations are physically identical at this moment, physics treats them as the same, even if their histories were wildly different. A short example makes this concrete. Think about a cup of coffee on a table. To predict what happens next, physics does not need to know who brewed it, what cafe it came from, or how tired you are. What matters is whether it is hot or cold, how much coffee is there, and the surrounding room temperature. If two cups match in those properties, physics predicts the same cooling behavior for both. The story behind them disappears. Only the present description remains. That present description is the state. This idea reaches far beyond coffee. A moving ball, a gas in a room, a planet in orbit, all of them are treated the same way. Physics asks a single question: what information is required to fix the future behavior? Everything else is ignored, not out of laziness, but because it has no physical effect. This is where people often hesitate. It feels like something must be missing. Surely reality carries more detail than a short list of numbers. Yet experiments keep agreeing with physics. If a detail cannot influence what happens next, it does not belong in the state. A state is not a photograph. It is a working summary. It contains exactly what the laws of nature can act on, and nothing more. That makes states powerful and also a little unsettling. It means the universe carries itself forward moment by moment without consulting its past except through what the current state already holds. Everything that can happen next depends on what fits into that description and nothing else. So let's slow this down and take it apart carefully, because this is where the word state stops sounding ordinary and turns into something precise. At the most basic working level, a state is the complete physical condition of a system, expressed in a form that allows the laws of physics to operate without guessing. It is not a picture, not a label, and not a story. It is a set of facts that fully fixes what the system can do next. That word complete is doing real work here. Complete does not mean detailed in a human sense. It does not mean rich, expressive, or emotionally satisfying. It means that if you hand this description to the laws of physics, they do not ask for anything else. No extra information, no missing inputs, no follow-up questions. If some detail can affect what happens next, it belongs in the state. If it cannot, it does not. That rule sounds obvious until you apply it seriously. Return briefly to the coffee. Suppose 2 cups sit on the same table. One was brewed 5 minutes ago, the other an hour ago. One was stirred clockwise, the other counterclockwise. One came from a cafe, the other from a kitchen. None of that enters the state. If the temperature, the amount of liquid, and the surrounding air are the same, physics predicts the same cooling behavior. The rest feels important to us, but it has no physical leverage. That difference between what feels real and what can influence future behavior is where many people get lost. Physics has learned to be ruthless about it because prediction depends on it. This tells us something crucial about what a state actually is. A state is not how things look, it is how things are positioned relative to the rules. That is a very different notion. It trades rich description for functional sufficiency. This is why states so often look like a short list of numbers, not because reality is simple, but because most details cancel out when it comes to future change. People often expect that more description should always improve prediction. Physics finds the opposite. Extra description often adds noise without adding power. States are minimal on purpose. Now follow the consequences of that idea. Any change you can think of, motion, heating, mixing, decay, growth, can be described as a transition from one state to another. The laws of physics are nothing more than rules that map one state into the next. This reframes the entire structure of physics. Instead of objects being pushed around by laws, you get states being updated by rules. Instead of causes acting on things, you get present conditions fixing future conditions. Take memory. People often speak as if physical systems remember their past. Physics says something stricter. Any trace of the past must be encoded in the current state. If it is not encoded there, it has no effect on what follows. A stretched spring carries information about being stretched because its present shape contains it. A scar carries information about an injury because the tissue structure contains it. A cooled cup of coffee carries no information about how hot it was an hour ago because nothing in its present condition encodes that fact. Memory in physics is not a mysterious faculty. It is information stored in a state. This leads to a result many people resist. The past has no direct influence on the present. Its influence exists only through what survives in the current state. If nothing survives, the past is physically silent. This is not a philosophical preference. It is forced by how prediction works. If 2 systems share the same state, physics gives them the same future. No experiment has ever contradicted this. Now let's push deeper into what a state is, not just how it behaves. A state is an abstract object. That word often raises eyebrows, but here it means something very specific. The state is not located in space the way the system itself is. The system exists in space. The state exists in the space of possible conditions. Those are different arenas. A ball travels through space. Its state lives in a mathematical space whose coordinates represent position and motion. A gas fills a room. Its state lives in a space defined by quantities like temperature, pressure, and density. The system and its state are related, but they are not the same thing. This distinction becomes important as systems grow large. A gas contains an enormous number of particles, far too many to track individually. Still, it has a state. Physics uses collective quantities because they preserve predictive power. The full microscopic detail exists, but the state that physics actually uses is compressed. This reveals another sharp lesson. A system always has a state, even when no one can write it down. Existence and accessibility are not the same. Weather has a state. We measure parts of it, approximate others, and still get surprises. The laws did not fail. The description was incomplete. This reframes uncertainty in a very concrete way. Uncertainty is not something floating over reality. It is a mismatch between the actual state and the state we are able to specify. Physics never becomes confused. Descriptions do. This also explains why physics places so much emphasis on initial conditions. Laws by themselves do not produce specific outcomes. They only specify how states change. Without a state to act on, laws describe possibilities, not events. People often ask why the laws of physics do not explain everything. The answer is blunt. Laws do not select states. They transform them. The universe does not ask the laws what state to be in. It already is in one. Now bring this picture into modern physics. In quantum mechanics, the state takes a form that resists everyday language. It does not assign definite values to properties like position or motion. Instead, it encodes the full structure of possible outcomes. Yet its role remains unchanged. The quantum state still contains everything physics can say about what follows. Nothing extra can be pulled from it. Nothing less will suffice. This result bothered many brilliant physicists. They suspected hidden layers beneath the formalism. Decades of experiments answered the same way. Predictions match the quantum state exactly, and no hidden layer reveals itself. Once again, physics encountered the same lesson. Reality provides exactly the information it uses, and no surplus. Here, the idea of a state stands out as more than a technical detail. It holds the structure of physics together. The universe advances by carrying forward a compact description of itself. Each moment inherits only what the present state contains. Everything else drops out of physical relevance. This does not make reality thin, it makes it efficient. And now something subtle but powerful comes into view. If the state contains all that can influence what follows, then the question, what exists, quietly transforms into what can affect future change. In physics, existence and influence are inseparable. That single move explains why some things that feel important never appear in equations, while some abstract symbols carry enormous predictive force. Physics follows influence, not impression. State is not jargon at all. It is the mechanism by which nature carries information forward in time. And with that backbone in place, a further tension comes into view, one that appears when the very notion of a single definite state begins to strain under. From here, the idea of a state stands at the center of how physical influence is organized. If influence must pass through the state, then anything that fails to register there cannot affect what follows. This draws a hard boundary around explanation. Physics does not ask what might have played a role. It asks what is encoded right now in a way that constrains the next moment. This changes how cause and effect are treated. Causes are not events reaching forward from the past. They are features of the present state that limit what can happen next. Effects are not produced by history pushing forward. They are produced by rules acting on current conditions. That view clashes with everyday habits of thinking. People tend to place causes in stories about what happened earlier. Physics places them in the present description. This difference is structural, not linguistic. Now look at systems where states react strongly to small differences. In chaotic dynamics, extremely tiny variations in the state lead to wildly different outcomes. Weather illustrates this well. Two atmospheric states that differ by amounts far below any practical measurement can lead to entirely different futures. The rules remain exact. Nothing about the laws breaks. The difficulty lies entirely in the state itself. Here is the striking result. Rule-based evolution survives even when prediction fails. The system follows its laws perfectly, yet foresight collapses because the state cannot be specified with enough precision. Unpredictability in this sense does not signal disorder, it signals sensitivity. This separates two ideas that are often mixed together. Lawfulness describes how states lead to states. Predictability describes whether those transitions can be tracked with the information available. One can hold without the other. Now move to smaller scales. Quantum physics accepts the same framework and then stretches it in a way that defeats familiar expectations. The quantum state does not list properties as fixed facts. It does not supply a definite position or motion ahead of interaction. Instead, it encodes how the system can respond when interaction occurs. This is not vagueness, it is precision of a different kind. The quantum state contains everything that can shape outcomes. It simply refuses to supply values that have no physical role until interaction takes place. This leads to one of the most surprising consequences in physics. The same state can give rise to different outcomes depending on how it is probed. The outcome is not stored in advance, it is selected through interaction. For a long time, many physicists expected a deeper layer that would restore familiar descriptions. Experiments repeatedly blocked that route. Predictions drawn from the quantum state matched reality exactly, and no hidden layer ever showed itself. Here, the meaning of a state sharpens further. It is not a list of attributes. It is a constraint on possible futures. Nothing outside that constraint appears in outcomes. This reworks causation again. There is no side channel through which influence travels beyond the state. No invisible mechanism supplements it. Influence passes forward only through what is encoded at each moment. This also explains why higher-level sciences remain valid without conflict. Chemistry, biology, and neuroscience all describe states, just not microscopic ones. A chemical state summarizes bonding arrangements. A biological state summarizes metabolic activity. A neural state summarizes electrical and chemical activity across networks. Each level tracks influence relevant at its scale. None violate physics because each respects the same rule. Future behavior is limited by present conditions. Reduction does not erase these descriptions, it anchors them. Now a natural puzzle emerges. If states carry everything relevant, and if laws act uniformly, why does the future ever feel open? Why does novelty appear at all? The answer lies in complexity rather than indeterminacy. Even systems governed by strict rules can generate behavior that resists anticipation because the space of possible states is enormous. Rules apply locally, but their repeated action produces outcomes that exceed simple forecasting. Nothing extra is added. What already exists rearranges itself in ways that overwhelm tracking. This explains why surprise persists even in a lawful universe. Surprise reflects limits on access to states, not failures of the rules. At this stage, the idea of a state carries weight beyond calculation. It implies that reality advances by carrying forward exactly what can influence what follows, no more and no less. The universe operates with strict economy. That economy explains both the reach and the restraint of physics. Reach comes from focusing only on influence. Restraint comes from ignoring everything else. The picture that emerges is stark but coherent. Reality is not driven by hidden narratives or accumulated intentions. It proceeds through continuous updates of states under fixed rules. Every moment inherits a complete description of what can shape the next one. Everything else, no matter how compelling, plays no role. This does not strip the world of richness. It explains how richness arises without extra machinery. With this framework in place, one issue stands ahead. Measurement itself must be treated as a physical process, subject to the same rules and the same limits. That issue waits just beyond this point. Measurement brings the framework to completion without adding anything new to the rules. When a system interacts strongly with another system, the two no longer carry separate descriptions. Their physical conditions become linked. From that point onward, there is a single, combined description that governs what can happen next. This is not a special category of event. It is the same kind of update that occurs in every physical process. Measurement does not reveal a pre-written answer. It creates a new situation by coupling systems together. This fact removes a long-standing confusion. There is no divide between natural evolution and observation. Both are physical interactions. Both follow the same laws. Both operate by updating states. With that, the picture closes cleanly. Physics rests on a small set of claims that have survived every test placed against them. Every physical system carries a complete description of its current condition. The laws of physics operate only on that description. What happens next depends only on that description and the laws. Anything not present in that description cannot influence future behavior. These statements are not philosophical positions. They are the conditions required for prediction, explanation, and consistency to function at all. There is also a crucial distinction that keeps reappearing across physics. A system can have a well-defined description even when no one can specify it fully. Limited access restricts forecasting, not the behavior of the system itself. Nature does not wait for complete information in order to proceed. This explains why lawful behavior continues even in situations where outcomes appear surprising or irregular. There are also boundaries worth stating clearly. Physics does not claim that current descriptions of states are final. Classical descriptions were replaced by quantum ones. Future theories may alter the form again. What cannot be removed is the role these descriptions play. They carry all physically relevant influence forward. Physics also does not claim to explain why the laws take their particular form. States describe how change unfolds under given rules. The origin of those rules remains beyond experimental reach. And physics does not require a single, uniform description across all scales. Instead, it supports compatible descriptions at different levels, each tracking influence appropriate to its domain. These limits are not weaknesses. They define where physics is precise and where it remains silent. Now assemble the full view. The universe is not best captured as a collection of objects accumulating properties through time. It is better captured as a continuous progression of physical conditions, each one determining what can follow. Laws act as update rules, transforming one description into the next. Nothing outside that process plays a role. This explains why physics favors compressed descriptions. It explains why distant histories fade while present conditions dominate. It explains why chemistry, biology, and neuroscience coexist without conflict, each using descriptions suited to their scale while remaining physically grounded. It also explains why explanation has sharp limits. Physics can state what follows from what and what cannot follow at all. It does not promise narrative satisfaction. It promises internal consistency. The takeaway is direct. Reality advances by carrying forward only what can influence what comes next. If something shapes the future, it appears in the current description. If it does not appear there, it has no physical effect. That single principle replaces countless informal assumptions with one disciplined framework. The world then reads not as a buildup of past events, but as a continuous handoff, each moment passing forward exactly the information required for the next, and nothing beyond that.
Never be ashamed to ask simple questions. While many try to look smart, it's often the ones labeled as fools, those who dare to ask silly questions, who uncover truths no one else has the courage to explore. All the great names in history, scientists, entrepreneurs, leaders, and thinkers, have one thing in common: curiosity. It was curiosity that pulled us out of caves and carried us to the stars. It was curiosity that made someone look at fire and wonder, what if I could control this? Every leap in our evolution, every step in our story was born from someone who dared to ask the question others were too afraid to ask. Curiosity is the greatest human talent, the silent engine that turns doubt into discovery, ignorance into knowledge, weakness into power. Now let me ask you something. How many times have you held back from asking a question because you were afraid of being judged? That shame is exactly what keeps most people trapped in mediocrity. If curiosity was strong enough to pull us out of the darkness of prehistory, to help us create language, science, technology, and even explore space, what can it do for your life today? Curiosity is like an eternal flame burning inside of us, but too many let it die out in the name of routine, rush, or the vanity of pretending to know everything. True success isn't about looking smart. It's about having the courage to admit you don't know, and the humility to put yourself in the position of a learner. Now imagine something that could change the way you see the world. Most people just keep repeating ideas, copying opinions, accepting ready-made answers without ever questioning them. It's like they're all walking in a line, staring only at the back of the person in front of them. But the curious refuse to live that way. They step out of line, raise their heads, look around and ask, is there another way? Why is everyone walking in this direction? Pay close attention now, because this is where the power of thinking differently is born.
Curiosity frees you from the prison of repetition. While the crowd settles for, this is how it's always been, the curious are guided by a single question. What if it could be different? It's in this small detail that we find the great difference between those who follow and those who lead. Every successful man and woman you admire has this in common. They aren't satisfied with superficial answers. They dig deeper, investigate, explore. They have the courage not to believe the first answer, to doubt what seems obvious, to question even what looks unquestionable. Don't ever accept memorized formulas without deeply understanding why each thing works the way it does. That's the mindset that can revolutionize even what others believe to be absolute truth. The curious think differently because they dare to step out of line, and the curious prosper because they see opportunities that the conformists could never imagine. Think about this. How many fortunes were built by someone who had the courage to ask, why not, when everyone else was saying, it can't be done? That is the power of curiosity applied to independent thinking. Those who follow the crowd only get as far as the crowd is gone. But those who think differently, guided by curiosity, carve paths no one else imagined existed. Are you ready to stop being just one more in the crowd and start seeing what others can't? Most people only see problems, obstacles, and limitations, while the curious see hidden opportunities in every detail. Pay close attention now. What sets great entrepreneurs, scientists, and leaders apart isn't just technical knowledge. It's the ability to look at the same situation everyone else sees and discover something entirely new. Curiosity turns barriers into hidden doors. When everyone says there's no solution, the curious ask, but what if there is? And it's in this simple act of questioning the impossible that revolutionary ideas, million-dollar businesses, and discoveries that change history are born.
Think about Thomas Edison facing darkness. Thousands accepted living by candlelight, but he asked, what if I could create a controlled light? Think about Steve Jobs looking at giant computers. Everyone accepted they were only for a few, but he asked, what if everyone could have one in their pocket? The curious don't accept the world as it is. They imagine the world as it could be. And that imagination, fueled by questions, opens doors that seem invisible to ordinary eyes. Do you see the power in this? Curiosity isn't just a tool for learning. It's a lens that reveals opportunities most people ignore. That's why curious people thrive. While others complain about difficulty, they discover hidden treasures inside them. Now imagine looking at your own life. How many problems seem like insurmountable walls? But what if, instead of complaining, you asked, what can I learn here? What opportunity is hidden inside this? That simple shift in perspective can turn failures into springboards, losses into valuable lessons, and moments of crisis into seeds of wealth. The curious see doors where others only see walls, and those who walk through those doors reach places that only a few will ever have the courage to explore. Pay close attention now. Thinking differently from everyone else isn't a gift reserved for geniuses. It's a choice. Curiosity is the key that opens that door, but it takes courage to walk through it. Most people live trapped in repeated patterns. The same thoughts, the same explanations, the same solutions.
But the curious break that cycle. They don't accept that's just the way it's always been. Instead, they dare to ask, what if it were another way? Now imagine something powerful. Everyone looks at a wall and sees only a limit. The curious one, instead of stopping, asks, what if I climb over it? What if I dig underneath? What if this wall is only an illusion? That simple mental exercise is what separates great innovators from the rest of the crowd. That's what it means to think differently, not being content with the shell, but digging into the core. And you can train yourself to do this every single day. How? First, don't accept ready-made answers. Always ask, why is it this way? What would happen if it were the opposite? Second, question your own certainties. The most dangerous ideas are the ones you never dare to doubt. Third, simplify. If you can't explain something clearly, it means you don't truly understand it. This is the technique that allows anyone to learn quickly and even teach better than so-called experts who overcomplicate what should be simple. Do you see the power in this? Those who think like the majority get the same results as the majority, but those who think differently, guided by curiosity, discover shortcuts, create new solutions, and find hidden opportunities. The crowd runs in circles. The curious draw straight lines toward the future. And now I ask you, are you willing to abandon the safety of following the crowd, to live the freedom of thinking for yourself? If you truly want to set yourself apart, you must turn curiosity into a daily discipline. Imagine this. Every day you wake up with a flame inside you, but if you don't feed that flame, it goes out. What keeps the greats ahead isn't occasional curiosity. It's living with it as a constant habit. Ask yourself, what didn't I understand today? What question was left unanswered? What can I investigate instead of just accepting? Practicing this daily creates a sharp mind, one capable of learning 10 times faster than average. Leonardo da Vinci made this a ritual. He wrote down questions, examined the simplest things, and broke down ideas until he truly understood them. You can do the same. Always carry a question notebook. Don't be afraid to write down doubts that seem silly. At the end of the day, choose one and go after the answer. This discipline creates a spiral of growth that never stops. Think about it. If every day you answered just one new question, in a year you'd have more than 300 answers most people never sought. And those answers become fuel for opportunities, better decisions, and bigger achievements. Curiosity is like a muscle. The more you train it, the stronger it gets. Turned out into routine, investigation into habit, questioning into a way of life. And remember, it's not about chasing perfect answers. It's about refusing to settle for the obvious. Those who cultivate curiosity every single day build a mind that cannot be stopped. Imagine with me something that could change the way you live forever. Every innovation, every breakthrough, every achievement that transformed the world began with a curious mind that refused to accept reality as it was. Pay close attention now. The curious don't wait for the future to arrive. They build it. It was curiosity that led explorers to cross unknown oceans, scientists to question dogmas, and entrepreneurs to reinvent markets. And it's curiosity that can lead you to create the future of your own life. While most people are content to repeat, the curious dare to imagine. While others wait, the curious take action. While others say it can't be done, the curious ask, how can it be done? That's the difference between those who merely survive and those who thrive. The curious not only learn more, they live more, because every day becomes a laboratory, every conversation an opportunity, every challenge an invitation to grow. Do you understand the power of this? If you choose to live with curiosity every single day, you will build a mind that cannot be imprisoned by routine, that is unshakable in the face of problems, and limitless when it comes to opportunities. Fortune doesn't belong to those who claim to know it all, but to those who never stop asking questions. Abundance doesn't come to those who fake certainty, but to those who are constantly in search of answers. So I want you to declare it right now, with courage. Leave a comment below. I will never stop asking why. Because that simple choice, repeated over and over, is the seed of an extraordinary life. Don't forget to like this video to support our work, and subscribe to the channel for more content like this. Remember, curiosity is the secret, and those who choose to cultivate it become not only learners of the present, but creators of the future. The next step is yours.
Spring 1947. A 30-year-old physicist sits alone in a Cornell cafeteria, watching a student toss a plate in the air. The plate wobbles as it spins. Something about the way it moves catches his attention. He pulls out a napkin and starts calculating the relationship between the wobble and the rotation. 3 years later, that napkin calculation becomes the foundation for a Nobel Prize. But the path from a spinning plate to Stockholm reveals something most people get catastrophically wrong about genius. This story comes directly from Feynman's documented accounts in Surely You're Joking, Mr. Feynman, and his 1965 Nobel lecture, corroborated by Hans Bethe and other Cornell colleagues who witnessed this period. What happened in that cafeteria wasn't a sudden inspiration. It was the resolution of a crisis that nearly destroyed Feynman's career before it began. October 1945. Feynman leaves Los Alamos after helping build the atomic bomb. He accepts a prestigious position at Cornell University, recruited personally by Hans Bethe. On paper, everything looks perfect. In reality, Feynman is dying inside. His wife Arlene died of tuberculosis just months before Hiroshima. He's 27 years old and already feeling like a fraud. The war work consumed him with urgent problems that mattered. Now he's supposed to sit in an office and think about theoretical physics for no reason, except that universities expect it. He later described this period with brutal honesty. I couldn't do anything. I was completely depressed. The pressure builds daily. Cornell hired him as a rising star. They're paying him. They're waiting for brilliance. He sits at his desk trying to care about physics problems and feels nothing. The intrinsic joy that once made him solve puzzles for hours has vanished, replaced by obligation and expectation. He attends seminars and feels like an imposter. He reviews papers and finds them meaningless. The harder he tries to force productivity, the more paralyzed he becomes. This continues for months. Colleagues start noticing. Bethe checks in, concerned but patient. Feynman considers quitting physics entirely. He's burned out in the exact sense modern knowledge workers understand, trapped in the gap between external expectations and internal motivation. But something else is happening beneath the surface that he doesn't recognize yet. Then one afternoon in the cafeteria, a student throws a plate in the air, just horsing around. The plate wobbles and rotates as it flies. Feynman watches it and notices something strange. The medallion on the plate, the Cornell emblem, seems to rotate faster than the plate wobbles. Is that real or an optical illusion? He has no reason to care. This isn't important physics. It won't advance his career. It won't justify Cornell's investment in him. But for the first time in months, he feels curious. He goes back to his office and starts calculating. Not because he should, not because anyone asked, because he wants to know the answer. He works out the equations for a wobbling plate. The relationship between the wobble rate and the rotation rate emerges. The wobble is twice as fast as the rotation. The mathematics is straightforward, elegant. He feels something he hasn't felt since before the war. Pure pleasure in figuring something out for no purpose except that it's interesting. Excited, he finds Hans Bethe in the hallway. "I've figured out the wobbling plate," Feynman says, and explains the 2-to-1 ratio. Bethe listens politely, then asks the obvious question. "What's the importance of this? Why are you doing it?" It's the question Feynman has been asking himself for months, the question that's been paralyzing him. But this time, his answer is different. He tells Beth, "There's no importance whatsoever. I'm just doing it for the fun of it." Bethe shrugs and walks away. For anyone else, that response might have been crushing. Cornell didn't hire Feynman to play with cafeteria plates, but something shifts in that moment. Feynman makes a decision that will define his entire career. He later wrote, "I'm going to play with physics whenever I want to, without worrying about any importance whatsoever." The transformation isn't instant, but it's real. He starts following curiosity without justification. A problem strikes him as interesting, he works on it. A calculation seems fun, he does it. The spinning plate leads him to think about electron orbits. That's arbitrary, there's no logical connection, but the plate rotation reminds him of electron spin, so he starts playing with those equations. The electron work leads him back to old problems in quantum electrodynamics he had abandoned as too difficult. But now, he's not approaching them as important career-defining challenges. He's approaching them as puzzles. Over the following months, the playful calculations compound. The quantum electrodynamics problems that seemed impenetrable when he was trying to force solutions become tractable when he's exploring them for joy. He develops new mathematical techniques without worrying whether they're publishable. He follows tangents that don't make sense. And slowly, piece by piece, he reconstructs quantum theory in an entirely new way. This wasn't just about burnout recovery. This was about a fundamental misunderstanding that destroys most talented people before they achieve anything remarkable. The misunderstanding works like this. Society teaches us that important work feels like work. Significant achievements require discipline, sacrifice, forcing yourself through resistance. The path to excellence is paved with obligation. You identify valuable problems, then motivate yourself to solve them through willpower and responsibility. This logic sounds reasonable. It's completely backwards. What Feynman discovered in that cafeteria was that the causality runs the opposite direction. The spinning plate wasn't important, which is exactly why it was important. By removing the pressure of significance, he reconnected with the intrinsic motivation that makes sustained excellence possible. He didn't decide to work on quantum electrodynamics and then force himself to care. He played with physics until the play naturally led him to quantum electrodynamics, at which point it wasn't work anymore. The distinction matters desperately. When you force yourself to work on important problems, you're operating on willpower, which depletes. You can sustain it for hours, maybe days, occasionally weeks, but not the months and years required for genuinely difficult breakthroughs. Feynman spent 2 years in that post-war depression, trying to will himself into productivity. It didn't work because it couldn't work. Willpower is a terrible engine for creative intellectual work. But when you follow curiosity, When you work on problems because they genuinely interest you in the moment, you tap into a renewable resource. Feynman spent the next 40 years doing physics not because he should, but because he couldn't help himself. The difference in output is exponential. His Nobel Prize-winning work on quantum electrodynamics emerged directly from that spinning plate play. His work on liquid helium, quantum computing, nanotechnology, all of it flowed from the same principle. Follow what fascinates you right now. Trust that significance will emerge. Here's where it gets deeper. Feynman didn't just discover that play leads to productivity. He discovered why conventional approaches to important work create the opposite of what they intend. When you label something as important, your brain activates threat response systems. You start worrying about failure, judgment, wasted resources, reputation. These systems evolve to keep you alive, not to make you creative. They narrow your focus, make you risk-averse, trigger perfectionism and procrastination. You freeze, exactly as Feynman froze at Cornell. The paradox is that by removing importance, by treating quantum electrodynamics as no more significant than a wobbling plate, Feynman lowered his psychological stakes enough to actually think clearly. The play wasn't a vacation from real work. The play was how real work happens. He later said, "Physics is like sex. Sure, it may give some practical results, but that's not why we do it." This principle extends far beyond physics. The same pattern destroys knowledge workers across every field. You identify an important career goal, a significant project, a problem that matters. Then you try to force yourself to work on it. You create accountability systems, deadlines, motivation techniques. The more important the problem, the more resistance you feel. The more resistance you feel, the more you conclude you need better discipline. You're solving the wrong problem. The issue isn't insufficient willpower. The issue is that importance triggers psychological mechanisms that make genuine creative work impossible. The solution isn't to abandon ambition or reject responsibility. The solution is to engineer situations where the work you find intrinsically fascinating happens to align with valuable outcomes. Feynman didn't stop caring about physics. He stopped caring about whether any particular piece of physics was important. That subtle shift changed everything. Consider your own experience. Remember a project where you got completely absorbed, where hours vanished and you couldn't stop thinking about it even when you tried. That wasn't discipline. That was intrinsic motivation. Now, remember a project where you knew you should work on it, where it was important for your career or income or reputation, but you kept procrastinating and forcing yourself forward. Same person, same brain, opposite results. The difference wasn't the difficulty of the work. The difference was whether you cared about the work itself or about the consequences of the work. Most career advice tells you to identify valuable skills and force yourself to develop them. Feynman's spinning plate reveals why that fails. You can't sustain forced effort long enough to achieve expertise. Instead, you need to find the intersection between what fascinates you and what produces value, then trust yourself to stay there. That sounds risky, like giving up control. But the alternative, trying to power through years of resistance on willpower alone, is what actually fails. The modern knowledge economy makes this even more critical. Information work has no physical constraints forcing you to stay productive. No one watches you think. You can spend 8 hours at a desk accomplishing nothing, and no one knows until results don't materialize months later. In this environment, intrinsic motivation isn't optional. It's the only reliable engine. Companies that understand this stop trying to motivate employees through carrots and sticks, and instead design conditions where people encounter genuinely interesting problems. The best careers aren't built by identifying lucrative fields and forcing yourself to excel. They're built by following curiosity until you accidentally become one of the few people who deeply understand something valuable. Feynman's later career validates this completely. He never took another project because it seemed important. When Caltech recruited him, he negotiated unusual freedom to pursue whatever interested him. When NASA asked him to investigate the Challenger disaster, he agreed not because space policy mattered to his career, but because he was curious about the technical details. He investigated by himself, talked to engineers instead of administrators, ran his own experiments, and discovered the O-ring problem that NASA was hiding. Then he insisted on including his findings even when the commission tried to suppress them. None of that would have happened if he was optimizing for career importance. It happened because he was following curiosity. The spinning plate principle also explains why so many talented people plateau early. They achieve initial success through some combination of ability and effort, then conclude they should double down on whatever worked. They professionalize, they optimize for visible metrics, they take on responsibility and importance, and they stop playing. The play was the engine generating the success they're trying to scale. By removing it, they guarantee stagnation. You see this everywhere. Researchers who stop doing actual research to manage labs, writers who stop exploring to build platforms, entrepreneurs who stop building to manage. They're all trying to preserve success by abandoning the mechanism that created it. The counter-argument is that play seems irresponsible. You have bills, obligations, people depending on you. You can't just do whatever interests you. But notice what actually happened with Feynman. By following the spinning plate, he became far more valuable to Cornell, far more productive, far more respected than he would have been by forcing himself through obligation. The play produced more of what everyone wanted from him. That's generally true. The market values rare, deep expertise. Deep expertise comes from sustained engagement. Sustained engagement requires intrinsic motivation. Therefore, the play isn't opposed to market value. It's the path to it. What matters is distinguishing between pleasure-seeking and curiosity-following. Pleasure-seeking is checking social media, binging television, any activity designed to produce dopamine without effort. Curiosity-following is engaging with questions that genuinely perplex you, even when the engagement is difficult. Feynman's plate calculation required work. He had to derive equations, check mathematics, think carefully. But it was effortless in the sense that he wanted to do it. That's the distinction. Intrinsic motivation doesn't make things easy. It makes difficult things sustainable. The tragedy is that most people never discover their spinning plate. They spend entire careers trying to care about what they think they should care about, wondering why discipline and motivation techniques don't work. They never try the other path. Pay attention to what naturally captures their curiosity. Follow it obsessively without justification. Trust that value will emerge. The risk feels enormous. What if you follow curiosity and discover nothing valuable? But the alternative, forcing yourself through decades of resistance, has already failed. Feynman died in 1988. His last words reportedly were, "I'd hate to die twice. It's so boring." Even terminal cancer couldn't make him pretend significance where he felt none. That consistency, that lifelong commitment to only doing what genuinely interested him, produced some of the 20th century's most important physics. The importance was a side effect. The curiosity was the point. The spinning plate that changed physics forever wasn't special. Any plate would have worked. What mattered was that Feynman gave himself permission to care about it without justification. That permission created space for genius to emerge. You likely have a spinning plate somewhere in your life right now, some problem or question that fascinates you for no good reason. The question isn't whether it's important. The question is whether you're brave enough to follow it anyway. What would happen if you stopped trying to care about what you should care about and started paying attention to what you actually care about? Feynman found out. The answer changed everything.
Time doesn't exist, at least not the way you think it does. Not as this universal clock ticking the same for everyone. That's an illusion. And once you understand why, you'll never look at your watch the same way again. Every clock on Earth is lying to you. The one on your wall, the one on your wrist. And I don't mean they're broken or poorly calibrated. I mean something much more disturbing. There is no such thing as the correct time. Now you might be thinking, wait a minute, that's ridiculous. We all agree what time it is. Noon is noon. Midnight is midnight. We synchronize our clocks and they all say the same thing. And yeah, sure, for everyday life, that works well enough. But here's the thing. It only works because we're all moving slowly. Very, very slowly compared to light. And we're all sitting in roughly the same gravitational field. The moment you change either of those conditions, your clock starts lying to you. Or more accurately, you realize it was never telling you the time. It was only telling you its time. Here's the secret. Time is personal. Time is local. Your clock measures your time. My clock measures my time. And these two times are not necessarily the same. So, let me explain what I mean by that. Because this isn't philosophy. This isn't some abstract idea you can argue about. This is measured. This is tested. This is real. Imagine you have two identical clocks, perfect clocks, the best clocks anyone could ever build. You synchronize them perfectly. They tick together. They agree completely. Now you take one of those clocks and you put it on an airplane. You fly it around the world, and then you bring it back and compare it to the clock that stayed on the ground. They don't agree anymore. The clock that flew is behind. It's ticked fewer times. It's measured less time. And this isn't because the airplane vibrations messed it up, or because the pressure was different, or any mechanical explanation like that. No. Time itself passed more slowly for the moving clock. Now watch. This was actually done. In 1971, scientists put atomic clocks on airplanes, flew them around the world in both directions, and compared them to clocks on the ground. The results matched the predictions exactly. Time runs differently depending on how you're moving. But wait, there's more. It's not just motion that affects time, gravity does too. A clock at the top of a tall building runs faster than a clock at the bottom. Not by much, we're talking billionths of a second. But it's real, it's measurable. The clock closer to the Earth, deeper in the gravitational field, ticks slower. So what does this mean? It means time isn't this universal thing flowing at the same rate everywhere. Time is flexible. Time is stretchable. Time is, well, personal. And this leads to something even stranger. The concept of now itself becomes meaningless. The twist, think about it. When you say right now, you're assuming there's some universal moment that applies everywhere. That right now, as you're listening to this, there's also a right now on Mars, a right now in the Andromeda galaxy, a simultaneous moment across the entire universe. If you're standing still on Earth, you have one definition of now. If you're flying past Earth at high speed, you have a different definition. Events that are simultaneous for you are not simultaneous for the moving person, and neither of you is more right than the other. This is hard to accept, I know. We grew up thinking of time as this absolute thing, this river flowing at the same rate everywhere, this background against which events happen. But nature doesn't care about what we grew up thinking. Nature does what nature does. And what nature does is far stranger than our intuitions. Here's why this matters. For most of human history, we thought space and time were completely separate things. Space was the stage. Time was the clock on the wall. They had nothing to do with each other. Then along came relativity and showed us that's completely wrong. Space and time are not separate. They're woven together into a single fabric. We call it space-time. And everything that happens in the universe happens in space-time. You cannot talk about where something is without also talking about when it is. They're part of the same measurement, part of the same reality. So let me give you an analogy. Imagine you're looking at a map. On this map, there's north-south and there's east-west, two different directions, perpendicular to each other. Now imagine two people standing in the same spot, but facing different directions. One person faces exactly north. For him, north and east are clearly different directions, no confusion. But then the other person faces northeast. For him, what he calls forward is partly north and partly east. His forward is a mixture of the first person's north and east. Neither person is wrong, they're just using different reference frames. What's purely north to one person is partly forward and partly sideways to another. Space and time work the same way. What looks like pure time to someone standing still looks like a mixture of time and space to someone moving. They're not separate things. They're different directions in space-time. And how you divide them up depends on your motion. That's the key. When you move through space, you're also affecting how you move through time. There's a trade-off. The faster you move through space, the slower you move through time. And this isn't a metaphor. This is literally what happens. Everything moves through space-time at the same total speed. Always. You can't avoid it. When you're sitting still, not moving through space at all of your motion through space-time is directed through time. Time flows at its maximum rate for you. But when you start moving through space, some of your space-time motion gets redirected. Less of it goes through time. So time slows down for you compared to someone who's standing still. Now you might ask, okay, but if time slows down when I move, why don't I notice it? And that's a great question. The answer is because everything slows down together. Your clock slows down. Your heartbeat slows down. Your thoughts slow down. Every process that could possibly measure time slows down by exactly the same amount. So from your perspective, everything feels normal. It's only when you compare your experience to someone else's, someone who is moving differently, that the difference shows up. Your clock and their clock no longer agree. Your time and their time have diverged. And here's the shock. This isn't a small effect at high speeds. If you could travel at 99% the speed of light, time would slow down by a factor of about 7. 1 year for you would be 7 years for people back on Earth. Get even closer to light speed, 99.9%, and the factor becomes about 22. You could take a trip for a few years, come back, and centuries could have passed on Earth. You could outlive everyone you know. You could see the far future, not by living longer, but by having time pass more slowly for you while the rest of the universe ages. This is real. This is how the universe works. Time is not what you thought it was. Well, nature doesn't think in terms of space and time separately. Nature thinks in terms of space-time. And once you start thinking that way too, everything starts to make sense. Imagine you're driving your car on a road. The road goes north. You can measure how far north you've gone. Simple enough. But now the road curves. It starts going a little bit east as well as north. Now, for every mile you drive, you're not going a full mile north anymore. Some of your motion is being spent going east. The total distance you travel along the road stays the same. But how that distance gets divided between north and east, that changes depending on the direction of the road. Here's the truth. Space-time works exactly like this. There's a kind of distance in space-time, and everything travels through space-time. But how that travel gets divided between space and time depends on your motion. When you sit still, all your travel through space-time goes through time. You're not moving through space, so you move through time at the maximum rate. When you start moving through space, some of your space-time travel gets redirected into space. Less of it goes through time, so you age slower. Your clocks tick slower. Time dilates. It's not magic, it's geometry. It's the geometry of space-time. Now, this might sound abstract, so let me make it more concrete. There's a quantity in space-time that everyone agrees on. No matter how fast you're moving, no matter where you are, this quantity is the same. We call it the space-time interval. Think of it this way. In regular space, if I measure the distance between 2 points, I might get a different answer than you if we're using different coordinate systems. Maybe I'm measuring in one direction and you're measuring in another. We disagree about how far east something is or how far north. But the actual distance between the points, the straight line distance, that's the same for everyone. It doesn't matter how you orient your rulers. The distance is the distance. The key insight, space-time has something similar. There's an interval between two events, not just 2 points in space, but 2 events in space-time, meaning 2 locations that also have times attached to them. This interval combines both the spatial separation and the time separation. And just like the distance in regular space, this interval is the same for everyone. You might disagree about how much of it is space and how much is time, but the total interval, that's invariant. That's a fact of nature that doesn't change based on your perspective. So, when we say space and time are the same thing, we don't mean they're identical. Obviously, time feels different from space. You can walk backwards in space, but you can't walk backwards in time. There are differences. What we mean is that they're connected. They're part of the same geometric structure. You can trade one for the other, depending on how you're moving. But the underlying structure, the space-time itself, that's absolute. That's real. That's what nature actually cares about. But wait, we've been talking about motion. But what about gravity? How does gravity fit into all this? And this is where things get really interesting. See, for a long time, people thought of gravity as a force. You know, the earth pulls on you, you pull on the earth. There's this invisible rope connecting everything with mass. And for most purposes, that works fine. You can calculate orbits, predict falling objects, send rockets to the moon. But that picture is incomplete. It doesn't explain why gravity affects time. It doesn't explain why clocks at different heights run at different rates. Something deeper is going on. Here's what's really happening. Mass curves space-time. The Earth doesn't reach out and grab you with some invisible force. Instead, the Earth bends the space-time around it. And you, moving through that curved space-time, follow the natural path, which happens to curve toward the Earth. You feel this as falling. But really, you're just moving in a straight line through curved space-time. It's the space-time itself that's bent. And here's the beautiful part. Because space-time includes time, when space-time is curved, time is curved too. Near a massive object where space-time is more curved, time runs slower. Not because some force is acting on your clocks, but because the very fabric of time is stretched. Really think about that for a moment. Time isn't just affected by gravity. Time is part of what gravity bends. You know, people often think of curved space and have trouble visualizing it. What does it mean for space to be curved? Curved into what? But actually, that's the wrong question. Space doesn't have to be curved into anything. The curvature is intrinsic. It's a property of the space itself. Let me give you an example. Imagine you're an ant living on the surface of a balloon. You can only move on the surface. You can't go up or down. You can only crawl along the balloon's skin. For you, the balloon's surface is the entire universe. It's two-dimensional, but it's curved. If you walk in what feels like a straight line, you'll eventually come back to where you started. The surface wraps around. Now, we standing outside can see that the balloon is curved in three-dimensional space. But you, the ant, can figure out the surface is curved without ever leaving it. You can do experiments. You can measure angles of triangles. You can notice that the rules of flat geometry don't quite work. The surface itself has curvature, and you can detect it from the inside. Now watch this. Our space-time is the same way. It's curved. We don't need to ask, curved into what? Because the curvature is detectable from within space-time itself. We measure it by watching how clocks run at different rates, how light bends near massive objects, how objects accelerate toward each other without any force pushing them. This isn't philosophy. This is physics. This is measurable. And here's where time comes back in. The curvature of space-time near Earth is mostly curvature of time, not space. Space itself is barely curved at all near Earth. But time is significantly curved. That's why clocks at different heights tick at different rates. That's why falling objects accelerate. The time curvature is the dominant effect. So, when you drop a ball and watch it fall, what's really happening? The ball is moving through curved space-time. It's following the straightest possible path, what we call a geodesic, through that curved geometry. And because time runs slower closer to the Earth, that path curves downward. You think gravity is pulling the ball, but actually, the ball is just moving naturally through curved space-time. There's no force, just geometry. The twist here, this explains something that puzzled physicists for centuries. Why does gravity affect all objects the same way? A feather and a hammer in a vacuum fall at exactly the same rate. Why? If gravity were a force, you'd expect heavier things to feel a stronger pull. But they also have more inertia, more resistance to acceleration. These two effects exactly cancel. It seems like a coincidence, a very precise, very suspicious coincidence. But in the space-time picture, it's not a coincidence at all. Objects aren't being pulled. They're just moving through curved space-time. And the path through curved space-time doesn't depend on what the object is made of or how heavy it is. The geometry is the geometry. Everything follows the same curves. This is profound. Gravity isn't a force. Gravity is the shape of space-time. And time is part of that shape. So when I say time doesn't exist, what I mean is that time as this separate, independent, universal thing doesn't exist. Time as a river flowing at the same rate everywhere doesn't exist. That's an illusion created by our slow speeds and weak gravitational fields. What exists is space-time, this unified four-dimensional fabric that can be curved, stretched, and warped by the presence of mass and energy. Time is woven into this fabric, inseparable from space, relative to motion, affected by gravity. Your clock doesn't measure the time. Your clock measures its own journey through space-time. Nothing more, nothing less. And that's the truth. But if time is so flexible, if it's different for different observers, what's actually real? Is anything real? Or is everything just perspective? And this is where it gets beautiful. Because yes, some things are real. Absolutely, unchangeably, observer independently real. They're just not what you expected. The space-time interval between two events, that's real. Everyone agrees on it. The laws of physics themselves, those are real. They work the same way for everyone, no matter how fast they're moving. The speed of light, that's real. It's the same in all directions, for all observers, always. Here's the secret. What's relative is how you slice up space-time into space and time. That's a choice. That depends on your motion. But the space-time itself, the underlying four-dimensional geometry, that's absolute. It's like, time doesn't exist. At least not the way you think it does. Not as this universal clock ticking the same for everyone. That's an illusion. And once you understand why, you'll never look at your watch the same way again. Every clock on Earth is lying to you. The one on your wall, the one on your wrist. And I don't mean they're broken or poorly calibrated. I mean something much more disturbing. There is no such thing as the correct time. Now you might be thinking, wait a minute, that's ridiculous. We all agree what time it is. Noon is noon. Midnight is midnight. We synchronize our clocks and they all say the same thing. And yeah, sure, for everyday life, that works well enough. But here's the thing. It only works because we're all moving slowly. Very, very slowly compared to light. And we're all sitting in roughly the same gravitational field. The moment you change either of those conditions, your clock starts lying to you. Or more accurately, you realize it was never telling you the time. It was only telling you its time. Here's the secret. Time is personal. Time is local. Your clock measures your time. My clock measures my time. And these two times are not necessarily the same. So, let me explain what I mean by that. Because this isn't philosophy. This isn't some abstract idea you can argue about. This is measured. This is tested. This is real. Imagine you have two identical clocks. Perfect clocks. The best clocks anyone could ever build. You synchronize them perfectly. They tick together. They agree completely. Now you take one of those clocks and you put it on an airplane. You fly it around the world. And then you bring it back and compare it to the clock that stayed on the ground. They don't agree anymore. The clock that flew is behind. It's ticked fewer times. It's measured less time. And this isn't because the airplane vibrations messed it up, or because the pressure was different, or any mechanical explanation like that. No. Time itself passed more slowly for the moving clock. Now watch. This was actually done. In 1971, scientists put atomic clocks on airplanes, flew them around the world in both directions, and compared them to clocks on the ground. The results matched the predictions exactly. Time runs differently depending on how you're moving. But wait, there's more. It's not just motion that affects time. Gravity does too. A clock at the top of a tall building runs faster than a clock at the bottom. Not by much. We're talking billionths of a second. But it's real. It's measurable. The clock closer to the Earth, deeper in the gravitational field, ticks slower. So what does this mean? It means time isn't this universal thing flowing at the same rate everywhere. Time is flexible. Time is stretchable. Time is, well, personal. And this leads to something even stranger. The concept of now itself becomes meaningless. The twist, think about it. When you say right now, you're assuming there's some universal moment that applies everywhere. That right now, as you're listening to this, there's also a right now on Mars, a right now in the Andromeda galaxy, a simultaneous moment across the entire universe. If you're standing still on Earth, you have one definition of now. If you're flying past Earth at high speed, you have a different definition. Events that are simultaneous for you are not simultaneous for the moving person. And neither of you is more right than the other. This is hard to accept, I know. We grew up thinking of time as this absolute thing, this river flowing at the same rate everywhere, this background against which events happen. But nature doesn't care about what we grew up thinking. Nature does what nature does. And what nature does is far stranger than our intuitions. Here's why this matters. For most of human history, we thought space and time were completely separate things. Space was the stage, time was the clock on the wall. They had nothing to do with each other. Then along came relativity and showed us that's completely wrong. Space and time are not separate. They're woven together into a single fabric. We call it space-time. And everything that happens in the universe happens in space-time. You cannot talk about where something is without also talking about when it is. They're part of the same measurement, part of the same reality. So let me give you an analogy. Imagine you're looking at a map. On this map, there's north-south and there's east-west, two different directions, perpendicular to each other. Now imagine two people standing in the same spot, but facing different directions. One person faces exactly north. For him, north and east are clearly different directions, no confusion. But then the other person faces northeast. For him, what he calls forward is partly north and partly east. His forward is a mixture of the first person's north and east. Neither person is wrong, they're just using different reference frames. What's purely north to one person is partly forward and partly sideways to another. Space and time work the same way. What looks like pure time to someone standing still looks like a mixture of time and space to someone moving. They're not separate things. They're different directions in space-time. And how you divide them up depends on your motion. That's the key. When you move through space, you're also affecting how you move through time. There's a trade-off. The faster you move through space, the slower you move through time. And this isn't a metaphor. This is literally what happens. Everything moves through space-time at the same total speed. Always. You can't avoid it. When you're sitting still, not moving through space at all of your motion through space-time is directed through time. Time flows at its maximum rate for you. But when you start moving through space, some of your space-time motion gets redirected. Less of it goes through time. So time slows down for you compared to someone who's standing still. Now you might ask, okay, but if time slows down when I move, why don't I notice it? And that's a great question. The answer is because everything slows down together. Your clock slows down. Your heartbeat slows down. Your thoughts slow down. Every process that could possibly measure time slows down by exactly the same amount. So from your perspective, everything feels normal. It's only when you compare your experience to someone else's, someone who is moving differently, that the difference shows up. Your clock and their clock no longer agree. Your time and their time have diverged. And here's the shock. This isn't a small effect at high speeds. If you could travel at 99% the speed of light, time would slow down by a factor of about 7. 1 year for you would be 7 years for people back on Earth. Get even closer to light speed, 99.9%, and the factor becomes about 22. You could take a trip for a few years, come back, and centuries could have passed on Earth. You could outlive everyone you know.
If you think you're dumb, congratulations. You just proved you can think. Because the real fool is the one who never asks anything. You're not dumb. And I'm going to prove it to you right now. Every human brain, without exception, starts with the same foundation. No brain comes with a label that says smart or stupid. Physics shows us that the brain is just like any other muscle in your body. If you train it, it grows. If you neglect it, it weakens. There's no fixed destiny written somewhere saying one person was born a genius and another was born to fail. What actually exists are thought habits that either strengthen or weaken your mental power. Now, imagine you never trained one of your legs. What would happen? You'd probably look like those gym guys who only work out their arms and completely forget about leg day.
It would be weak, with no strength to run. But that wouldn't mean you were born without muscles. It would only mean you never trained them. The same thing happens with the brain. Most people simply don't train it the right way. They use their brain like a cheap calculator, not like a brilliant laboratory. That's why they feel slow, stuck, incapable. But the truth is, all it takes is changing the way you use your mind to realize you've got infinite potential inside you. Now pay close attention. The first thing you need to understand is that intelligence is not about memorizing facts. Intelligence is the ability to explain things in a simple way. The method is this. If you can't explain something to a child, you don't really understand it yet. And that's the first secret to proving you're not done.
When you learn something, try to explain it out loud, as if you were teaching it. That's how you start working out your brain. Just don't forget to train your legs while you're at it, all right? Your brain is forced to organize the internal mess. It takes scattered bits of information like loose Lego pieces and has to build them into a coherent castle. This activates different areas: memory, language, creativity. It's as if regions that usually work separately suddenly come together in a grand orchestra. When you try to explain what you've learned, you're not just repeating it like a parrot. You're rewriting the knowledge inside your own head. And here's the key. If you want to learn any subject more easily, simplify it. The brain loves to turn everything into complications. It almost feels like the harder something sounds, the smarter a person thinks they are. But real intelligence is taking what's complicated and making it so simple that even a child can understand it.
Want to see it in action? Take a look at this little monster of an equation. Beautiful, isn't it? Looks like something a NASA genius would scribble on a chalkboard. Just looking at it, most people freeze up and think, that's it, I'm dumb, I'll never get this. But the truth is, what's really happening here is simple. All of that is nothing more than a complicated way of representing basic relationships between numbers. For example, right in the middle of all that chaos, you could say, this is just a fancy way of calculating the difference of two squares. And when you simplify it, it's really just x plus y. What looked like a mysterious equation is simply a sum in disguise. And that's the secret. When you simplify, the brain breathes. It understands the essence. Math isn't about memorizing giant formulas. It's about recognizing patterns. And the same goes for any field: physics, biology, finance. If you learn to search for the essence, the why behind things, suddenly everything becomes clear. No one is dumb when facing a hard problem. What we really have are bad explanations, messy and overcomplicated, that turn something simple into a maze. But when you force your mind to translate things into simple terms, you realize the brain was never the problem. The problem was always the way you were trying to learn. And it's not just in math. We simplify in physics, too. Someone walks in with authority and says, the law of inertia describes that a body in motion tends to remain in motion. Sounds complicated, right? Want me to simplify? It's just this. If you kick a ball, it keeps rolling until something stops it. That's it. In biology, the same story. Someone says in a serious voice, photosynthesis is the biochemical process by which autotrophic organisms convert light energy. Phew, exhausting. Want the simple version? It's just the way plants invented to eat sunlight. Done. No mystery. And you know what's best about all this? This way of learning is actually more fun. Because let's be honest, traditional studying is boring as hell. It's like trying to memorize an entire phone book just to look smart. But when you learn to simplify, when you turn the complicated into something simple, that's when the real fun begins. That's the moment the genius is born, the one who enjoys asking questions, who smiles when discovering the why behind things, who takes pleasure in turning mystery into clarity. Learning is like playing, because when you're having fun, the brain doesn't see it as an obligation. It sees it as a game. And with games, we keep going. Have you noticed? You can play video games for hours without getting tired. But 15 minutes of a boring lecture feels like medieval torture. Why? Because games have challenge, curiosity, fun. When you bring that same spirit into your studies, you unlock a superpower. Imagine this. You take a tough math problem, or some crazy concept in physics, and instead of thinking, oh my God, I'll never get this, you think, okay, how can I turn this into a joke? How can I explain this to my 10-year-old cousin and make him laugh? In that moment, you stop being a slave to studying and start becoming its master. And then something magical happens. You actually start looking forward to the next problem. You get curious. You start laughing at your own discoveries. And it's at that exact point that the genius is born, when learning stops being an obligation and turns into fun. And here's the paradox. The secret of intelligence isn't memorizing answers, it's asking why. A person who asks too many questions might seem dumb to others, but what most people don't realize is that curiosity has been essential for every human discovery. If Isaac Newton hadn't asked,
Why did this apple fall from the tree instead of shooting up into the sky? Gravity might never have been formalized. Think about it. What everyone else saw as something ordinary, an apple falling, Newton turned into a question, and from that question came one of the most powerful laws in physics. Albert Einstein? He didn't create the theory of relativity because he memorized formulas. He started by asking, what if I could ride alongside a beam of light? What would I see? A crazy, almost childish question that any serious teacher would have called nonsense. But it was exactly that nonsense that opened the door to one of the most revolutionary theories in history. Even everyday inventions were born this way. Why does water heat up when it boils? Why can a piece of metal turn into an electric current? Why does sound move through the air? Every breakthrough that now feels obvious started with someone annoying the world by asking simple questions. What most people call stupidity is really just the inability to ask. And what they call genius is nothing more than stubborn curiosity. Newton wasn't magical. Einstein wasn't superhuman. They were just stubborn enough to keep asking when everyone else was saying, "We already know that, stop bothering us." And here's the turning point. Genius is born when you take seriously the questions everyone else ignores. If the apple falls, ask why. If the shadow moves, ask why. If a 500-ton airplane flies while a little bird drops dead from a tree, ask why. The more you let those stupid questions bother you, the closer you are to brilliance. And here's a truth almost nobody talks about. You're not dumb for asking. You're only dumb when you care too much about what other people think of you. Because that, deep down, is what kills curiosity. You wanted to raise your hand in class and ask, but then you thought, they'll laugh at me. They'll think I don't know anything. But guess what? It's exactly by not asking that you stay not knowing it. A genius is the person who simply doesn't care. He asks, he gets it wrong, he gets it right, he asks again, until he understands. And here comes a crucial point: emotional intelligence. There's no use in training your brain if you're still a slave to other people's opinions. A brilliant mind isn't just one that understands physics or math. It's one that understands itself. It's the kind of mind that doesn't get shaken by stupid criticism, doesn't compare itself to the neighbor, and doesn't fall apart because someone said, "That's obvious." Pay close attention now. Anyone who lives worried about judgment will never discover anything new. Every bold idea they have, their first thought is what their friends will say, what the family will say, what the experts will comment. The result? They spend their entire lives hiding their questions, and with them, hiding their true potential. You want to be seen as intelligent? Then stop trying to look intelligent. Focus on being curious, on simplifying, on laughing at your own mistakes, and on learning quickly. That is far more rare and far more valuable than pretending to know everything. In the end, the real genius is not the one with ready-made answers, but the one with the courage to ask, the discipline to search, and the maturity not to care about the audience. The same people who laugh at you today for asking will applaud you tomorrow for discovering what they never had the courage to look for. So, what should you start doing today to train your mind like a genius? First, cultivate curiosity. Ask why about everything. There's no such thing as a stupid question. There's only the fear of looking stupid. And you already know, you're not dumb for asking, you're dumb for caring too much about what others think. Second, practice simple explanation. Every time you learn something, try to teach it out loud as if you were explaining it to a child. If you can't, it means you don't really understand it yet. Go back, simplify it, and explain again. That's the workout that truly strengthens your brain. Third, take action. Just thinking isn't enough. Solve problems, write, test your ideas. Action is the final exam that shows whether you truly understood or if you were just memorizing. Fourth, practice concentration. Stop letting yourself get distracted every 5 minutes. When you focus on one single thing, your mind works like a laser. Fifth, build self-confidence. Don't wait for applause. Every genius has been called crazy at some point. The difference is they kept going anyway. Curiosity plus simple explanation plus action plus concentration plus self-confidence. That is the manual that proves you were never dumb. You just needed to learn how to use your brain the right way. And remember this,
Inside your head, you carry the same kind of brain that wrote symphonies, that built rockets, that discovered gravity, that decoded DNA. You have a brain capable of finding the cure for cancer, of creating technologies that don't even exist yet, of transforming your life and the lives of millions of others. The problem was never you. The problem was believing you were limited, that you had no talent, that you weren't born a genius. But the truth is, the genius has always been inside you, waiting for you to stop being afraid to ask, to stop going silent in front of what you don't understand. Never forget, every time you ask why, you open a new door inside your mind. Each answer leads to another question, and it's in that endless path that the greatest ideas are born. The world is not driven by those who know all the answers. It is driven by those who have the courage to ask the right questions. So please, never stop asking why. Never let shame or judgment kill your curiosity, because it's exactly that curiosity, that restless spark inside you, that can change everything. You're not dumb. You never were. You're an explorer, and your mind is the greatest unexplored territory that exists. Take care of it, train it, simplify, focus, trust, and keep asking, because every single why could be the beginning of the next great discovery. And now I want you to do something simple but powerful. Leave your comment down below. Write, "I will never stop asking why." Declare it, because every word you write is a commitment to your own growth. And don't forget to like this video, because that shows it truly resonated with you. Subscribe to the channel to keep receiving content that challenges your mind and expands your worldview. Think about it. Maybe a single click today could be the start of a massive transformation in your life. So comment, like, subscribe, and hit the bell. Because here you don't just get information, you get tools to think like a true genius.